Thank you. This morning I'm going to tell you about some of the work we've been doing and using software-defined networking to improve network management. This is the work of two grad students, Jun Kim and Srikant Sundarasan, who've been working a lot in this area over the past couple of years, as well as Marshani Chetty, who's a postdoc in human-computer interaction. And we were just hearing a lot about interfaces, and we'll see towards the end of the talk why, how we've been using SDN to improve interfaces that users actually see. So I've been working in network management problems for quite some time, and it's of course no secret here. I think we've seen this slide now 3 or 4 times and presented in different ways this morning. Network management is very, very hard. It's currently manual. It's error prone. It's very complex. Why is it hard? Well, I'm going to get into that a little bit in a little bit more detail. But one of the reasons it's very hard is that network configurations change continually. There's constantly provisioning of new users and new devices. So this is a graph showing, for example, the number of devices. This is the number of switches in the University of Wisconsin network over the course of 5 years. You can see that it's continually growing. Many of these are virtual, of course, but as the network continues to grow, operators are adding new devices, new users, new features. Complexity is just going up. It is not going down at all. Response to incidents is another thing. This is a sort of morning report that I grabbed from the Georgia Tech OIT webpage from Friday morning. You can see there were 2 network outage events that required some kind of operator intervention. So operators are continually tweaking the network. They're continually touching the configuration. And it should come as no surprise then that as operators are touching this configuration, they're introducing errors. And what I've been working on for the past 6 or 8 years now is to develop mechanisms to help network operators manage the networks better. And as we're talking about, we'll talk about enterprise networks, but we'll also talk about home networks where the network operator is unfortunately you. So I'm also interested in, we're going to talk about how to make your life better as well. So we've been talking a lot about software-defined networking this morning. We've heard about how software-defined networking makes it easier for network operators and protocol designers, et cetera, to evolve new network capabilities, to innovate in their network. And what I want to talk about in this talk is a slightly different question, which is, can SDN also help network operators manage their networks after they're deployed? Right, so what kinds of things can we do using SDN to make networks easier to manage? So SDN is great, but it's not a silver bullet unless we know what to do, right? So the first thing we need to figure out is why is network management so hard today, and then we can go back and sort of figure out what kind of changes we'd like to make. So I'd like to go through sort of posit 4 reasons why I think network management is hard, and sort of try to convince you with some examples why I think these are some of the major reasons the problem's so hard. The first is that configuration is very complex and low level. I've given you a taste of that already. Campus network, for example, might have more than 1 million lines of configuration, thousands of devices, switches, routers, firewalls, etc., and hundreds of thousands of changes every year. This is sort of a graph showing the time of day, the average number of changes that a network operator is making to a campus network in any given day. So, at peak time, tens of thousands of changes. Of course, some of those are automated with scripts, right? But still, we're talking about very low-level changes to switch and firewall configuration. This here is I grabbed this a couple days ago from RateMyNetworkDiagram.com. It's sort of like a hot or not for home networks. So this is somebody's home network. They've made a very nice diagram here, but if you can't read it, that's part of the point. I doubt, if it's hard for you to read, it's probably even harder for them to manage. Maybe got them a 10 out of 10, for aesthetics, but once something breaks, of course, it's very tricky for anyone to go in and fix. So that's one reason why network management is pretty hard. Another reason is that network state is dynamic, right? Things are constantly changing. Hosts are continually coming and leaving. Hosts may become infected. And unfortunately today, configuration is a pretty static notion. Operator makes some changes to configuration, commits them to CVS or RCS or what have you, pushes them to switches, and then something happens. Right, an infection occurs, or a host comes, a new host comes and needs to be authenticated, or an attack occurs. And the operator now has to do something. And rush, got to make a bunch of changes. And of course, none of these things are being vetted, and then all of a sudden, we've got a mess on our hands a week later when nothing works. Instead, what I'm going to propose is one of the things that SDN allows us to do is actually move some of the aspects of network configuration that are naturally dynamic into the configuration itself. So I'll talk a little bit about how we're going to do that with a system called Resonance. The third reason that network management is hard is because too much complexity is exposed. For example, if we're talking about configuring a home network today, this is the first tab that you might see. And if you and I are probably lucky enough to know what a MAC address is and what SSIDs and web keys are, but the average user probably is not, right? And this gets more and more complex as you sort of tab through these things. This is far too complex for the average user. So what I'm gonna pose later in this talk is that one of the things SDN can allow us to do is refactor some of the functions. One of the things that, as we've been working with researchers in human-computer interaction, one of the things that we've been realizing is that this is, perhaps designed by someone who drives a stick shift, but it's not entirely the fault of the interface designer. One of the things that interface designers, are crippled by is the underlying infrastructure. So what they have is a choice: do I hide this complexity or do I show it? Right? They don't have any flexibility as, maybe I should move some of this complexity to a different part of the system. And that's one of the things that SDN allows the designers to actually do, thereby improving, thereby offering the potential to improve interfaces as well. The last thing I want to talk about as far as a source of management complexity is that devices are heterogeneous. There are routers, switches, firewalls. There are many different middle boxes. There's authentication portals, there's vulnerability scanners, etc. Each one of these things has its own configuration. Each one generates its own type of alerts. It has its own interface. I mean, somehow this has to get all kludged together into something that actually works and makes sense. These devices have separate and often competing functions for performing different tasks. There's a whole hodgepodge here that has to work together. And because each one of these devices is sort of designed independently with its own protocols, interfaces, etc., it's sort of left to the operator to his own devices after the fact to sort of make it all work together. And what I'm going to posit is that one of the things SDN allows us to do is cope with this heterogeneity a lot better. So first I wanted to sort of tell you a story, not a long story, it's a one-slide story, was that Jen's talk really appealed to me, as sort of a new language to help operators configure networks. And actually, when I was working on my dissertation, I wanted to do a similar thing, and my advisor said, no one will ever adopt a new configuration language. This was, by the way, before SDN. But no one will ever adopt a new configuration language. What you should instead do is just, check the configuration that is currently in networks, check it for errors. People will find that much more useful. That's in some degree true. The tool that we developed was downloaded and used by many ISPs, and we found mistakes. But this was relatively unsatisfying, right? Because we were very limited in what we could do. The tool wasn't complete, and that just because the tool didn't raise any alarms did not mean the network was going to behave correctly, and it wasn't sound either. Meaning, just because the tool raised alarms didn't necessarily mean that wasn't what the operator actually meant to have happen, right? So a lot of the things we've been hearing about this morning, as far as let's have a language that helps an operator express what they want to have happen more directly in terms of policy and intent. Those are the types of things that I think would ultimately get us around the problems that we faced in this work. So when software-defined networking rolled around in 2005 roughly, and then sort of the incarnation of OpenFlow rolling around not long after, the idea then, of course, as we've seen, is to control the network from a logically centralized system, and then what that allows us to do is talk about configuration and policy as high-level programs. And we heard a little bit about that in the previous talk as well. And that's essentially what we're talking about here as well, which is that if we view network policy as a higher level program, that essentially decouples us from a lot of the nitty-gritties and a lot of the problems that I was mentioning before. I'm going to sort of walk you through how we solve each of, or how we approach each of those 4 problems in just a minute. But the high-level idea here is a platform that we're building called Resonance. And the idea here is that let's not configure the network. Let's not go around like expecting an operator to configure thousands of independently operating network devices with sort of the COBOL equivalent of network configuration. We've seen how well that works. And we've seen how well we can build tools to help network operators check for errors and among other things. So the idea is apply SDN to sort of allow operators to write network policies, write network protocols as programs. And the idea here is that in doing so, we can make policies more expressive, more predictable, more evolvable, and also, more importantly, more usable. So I'll talk about how we do each of these things through a couple of examples. First, I want to describe our general approach to tackling these problems. So as you recall, these are the 4 problems that I listed out before. One of them, the first was dynamic state, right? The network state is constantly changing. And what we do actually is extend we extend a Knox controller so that it also has this event listener that maintains a state machine. So for each device in the network, we maintain what state we think that device is in. For now, we can just think of that as an abstract state. I'll get more concrete when I talk about a specific policy in an enterprise network in just a minute. Low-level configuration, obviously, we can talk about instead configuring the network using a high-level policy language. There are, of course, many examples of doing that. Frenetic being one. I'll perhaps offer a sort of poor man's high-level policy language that we're using for Resonance right now. Ethane as well had another one. So there are many different instantiations here, and I think there remains work to be done. But that's sort of Resonance's approach there as well. The third is too much complexity was exposed, right? So I'm going to show you in a certain case in particular, when we get to talking about home networks, I'll show how we refactor some of the complexity so that the user doesn't necessarily have to see a lot of what we were seeing there. And then finally, coping with heterogeneity. There, of course, we're talking about standard control protocols. So, of course, from the controller controlling the switches, we know about the OpenFlow control protocol by now. But then the other thing, too, is that I mentioned we've got all kinds of devices in the network. We've got firewalls, intrusion detection systems, authentication portals, et cetera, all generating events, right? And we need a way of sort of processing those events. And for that, we have sort of a standard event processing framework by which we can sort of take action depending on what we hear from different devices in the network. So let me talk about each of those. So processing dynamic events. So the idea here is think about the network policy as essentially nothing more than an event-based program. So if we just had to configure a topology, provision some devices, and then be done with it, network management probably wouldn't be hard. What makes network management hard? Stuff is always happening, right? So, but we can cope with this stuff. What we can do is allow a network operator to express what they want to have happen when a certain thing happens, right? So if an intrusion alert happens, the program might decide to do something, right? Depending on whose device it is, whether or not it's a guest of the network or a high-level executive, you might want to take a different type of action. When a host registers, you might want to take a different kind of action. When an operator modifies policies, that might require other types of actions. We can express these as centralized programs. What I'm going to do then, or what Resonance does then is basically take that program, right, which is essentially an event processor, and maintain state for each device in the network. And here, each host or each device is associated with some kind of state and a security class. An example state might be this device is registered or appeared on the network, but it has not authenticated, right? So now network operators do a lot of complex things, which I'll describe, to put a host in a captive portal or garden wall until they've authenticated. We can do these types of things a lot easier by expressing them as a state machine, and I'll show you how. So we specify a state machine, then we specify the conditions or the events that trigger a host from moving from one state to another. What causes a host to move from a registration state to an authentication state? Well, presumably it receives some kind of event. it receives perhaps a notification from an authentication portal that a host has successfully authenticated. Right, so we specify states, we specify conditions for moving between different states in the network. And then finally, we specify what that forwarding state should be for each state. So for example, if a host is registered but not authenticated, maybe we want to pass port 80 traffic to a registration host or a captive portal. Maybe we want to allow DNS traffic through in DHCP, but we want to block everything else. Right? And then depending on who it is, depending on who authenticates, maybe we want to rate limit them, or maybe we want to cap them, right? So they don't use a particular amount, more than a particular amount of traffic in any particular day or time interval. Towards the end of the talk, I'll actually show you a cap management system we have that's actually running live in the room here. So as I mentioned, a way to cope with the low-level configuration is to come up with some high-level policy language. And as I mentioned, there are many ways of doing that. We saw one example in the previous talk. With resonance, because we're keenly interested in managing the states for each device, keeping track of the states, and then taking specific actions depending on what state each device is in, we basically have a language that specifies essentially that finite state machine. Standard controls, what do we do here? Well, as I mentioned, we've got an OpenFlow channel between our controller and the devices in the network, and then we've got a framework for processing events from different kinds of network devices. Refactoring functions. So as I mentioned, current interfaces primarily make decisions about whether or not to hide or display complexity. Do I show the user this thing about MAC addresses or SSIDs or channel settings or what have you, or do I hide it? Instead, what we can do is actually change where some of this function is placed. Potentially, in the case of a home network, you might not want it in the home at all, right? It could be a remote third-party controller, which is what I'll show you at the end of the talk. We can change where that function is placed to make the system more usable. I mean, and the sort of guiding design principle that we've been using for this is to hide most information. Right, so users mostly don't care about how stuff works, right? They just want it to work. So we're trying to only expose information if it improves situational awareness. That is, if it tells the user something about what's going on in the network that they need to know. For example, there's someone on my wireless network that appears to be no one who lives in my house. That might be something that improves situational awareness. The other thing is it's got to be actionable, right? The user should be able to do something about it. Someone's on my wireless network who shouldn't be here. Can I kick them off? Well, hopefully the interface allows you to do that. Otherwise, that information wasn't very useful. Right, so things that aren't actionable or don't provide useful information, we try to hide. In particular, we also try to hide the how, right, and show basically only the what. So now what I'm going to do for the rest of the time is describe to you and show you two case studies. The first is an example of how we solved an access control problem in in campus networks. In particular, this is a re-implementation of the way Georgia Tech currently does access control in the Georgia Tech campus. Today it's quite complicated and low level. I'll sort of walk you through some of the alphabet soup very quickly, and then I'll show you how we do this in a much simpler and more flexible way. The second thing I'm going to talk about is a system that we've built to enable the home network operator, that is you, to control usage of your home network a bit better. There are a lot of things that people want to control. For example, with the advent of caps, and people may want to control how devices consume those caps. They also may want to install things like parental controls. Today, this is just really hard, really, really hard. What we're trying to do is basically make this very intuitive and simple. And I'll show you where we are in that, in sort of making progress on that. So just a case study. How does access control work in the Georgia Tech campus network today? Well, it's very complex. I'll just sort of briefly describe. A machine with a new MAC address appears. The switch recognizes this new MAC address as being new. It asks this VMPS thing. Something about, hey, what should I do with this new MAC address? It says, okay, put this thing on a VLAN and give it a private IP. Okay, so now the host can only go to this web authentication portal. The host then authenticates there and then okay, the web portal sends this request thing to this, or the result of this authentication to the VMPS, and then, okay, VMPS tells the switch, okay, move this over to the public IP, and then here's the great part. After all that, the user has to reboot, because there's no guarantee that the user can get a new IP address, right, without sort of re-DHCPing. And the easiest way for the operators to guarantee that the user is getting a new IP address and re-DHCPing is to actually just reboot their machine. So they have very little control over what's going on, right? So after all that acrobatics, you've still got to ask the user to reboot. Worse, what happens when we need to do something with this machine? What happens when an infection occurs, right? Or what happens when we need to quarantine this box for any reason? Then we're deeply out of luck, because we can't move this guy back to the private VLAN, because we've got to force that machine to get a private IP address again. Excuse me, your machine appears to be infected. Can we reboot you so that we can put you back on the private VLAN so that you can't have internet access anymore? Yeah, probably not going to happen. Right, so the operators basically throw up their hands. They said, hey, can you help us with this? And that's basically where we started thinking about what are the problems here and how can we solve them. One of the problems is that access control is too coarse-grained, right? It's quite static, it's inflexible, it's prone to misconfiguration, and we've got to rely on VLANs to isolate these infected machines. The other thing is it's very difficult to dynamically remap hosts to different portions of the network. You know, anything that requires a DHCP request requires a Windows user or many users to reboot. And then monitoring also is not continuous, right? It's not well integrated with the dynamic policies, right? So an intrusion detection system might notice a vulnerability or a compromise and want to move that machine to a garden wall or a place where they can only download patches. This is the type of thing that is just very, very hard for operators to do today. What we did then is to say, well, what if we just redesign this with SDN? What would we do? Well, let's go back and think about the fact that networks are basically just event processors, right? They're just things that recognize that there are things on the network whose states are changing. Well, can we express each host as, can we express the state of each host in a simpler way? Well, yes, we can, actually, and this is what we did. In an OpenFlow controller, what we did is actually encode a state machine that we want to use to represent the state of each host. And we said, okay, well, first the host appears, that new MAC address comes on the network. It's in a registration state. If we see a successful authentication, say from a web authentication portal, well, we just basically tell the controller, move that host to an authenticated state. If it's failed, of course, we quarantine it. Other thing the operator wants to do is scan the host, make sure it's clean before it gets, basically, unleashed on the network to, infect or not infect, hopefully, everyone else, right? So scan the network, scan the host. If the scan comes out clean, move it to this operation state where essentially the host is sort of free to run wild at that point. If later a vulnerability is detected, well, no problem. The IDS or the vulnerability scanner can just tell the controller, hey, I noticed that this host appears to be infected. Will you change the state of that host? No problem. Controller basically updates its view of the state of that host, and then that controller basically then pushes the corresponding flow table rules to the switches to do the right thing. Okay. So we have a deployment of this in the Georgia Tech campus network. We're using it in our lab. There are a couple other labs on campus that have this deployed. So this is something that we've basically got running in operation across 3 buildings in the Georgia Tech campus. Another case study, second case study, as I mentioned, is usage controls in home networks, right? So network management in homes is already pretty challenging, and it's getting worse, right? The number of devices that we have that are Wi-Fi enabled or some way trying to connect to the network is only increasing. And not only are the number of devices increasing, but the things we want to do with the network are getting more and more complex, right? So it's not just enough that, hey, everything's on the network, right? And we're happy. Hey, I can browse the web. Isn't that great? No. I actually want to make sure that that my kid can't get on Facebook after 9 p.m. Or I want to make sure that with this bandwidth cap that no more than a certain fraction of my usage is devoted to Netflix. Or I'd like to see how much traffic is coming from my roommates using BitTorrent. I want to make sure that whenever I pick up the phone to do Vonage call or Skype call, that they're BitTorrent isn't going to clobber my VoIP call. Well, these are the kind of things that we want to do now, right? And we can't do them, right? It's just too hard. So I want to talk about, in particular, about usage caps, right? So these things are a reality now. Comcast and AT&T have usage caps. There's, of course, uproar about 250 gigabytes being just terribly low. Let me remind you that Rogers in Canada has this great gold-plated plan which gives you 60 gigabytes a month. So just one more reason it's great to be in the U.S., right? But usage cap management is a real problem. And basically what we did, and we started thinking about this problem, and we said, hey, wait a minute. This is the same problem that we just solved with access control in enterprise networks. It's the same thing. It's like we've got devices in the home. We need to decide like whether or not they've got access to the network. And then, if a particular device uses more than its allocated amount, we want to cut it off. Or if 9 p.m. hits, I want to cut that particular destination off. I don't want to allow web traffic to Facebook anymore. These are just events again, right? So it's the same problem. So what we did is we took this resonance controller, which we had deployed in the Georgia Tech campus network, and we basically just made it a home network controller. And here basically what we have is we've basically got a home gateway router, Netgear router. There's one sitting in the back of the room on that table. And it's actually, I'm connected to it right now. I'm connected to that, to the internet. And my router that's sitting in the back of the room is basically speaking to this resonance controller that's basically sitting back at Georgia Tech and tracking my usage. Let me see if I can show you that, if all goes well. Okay, so let's go here. Okay, this interface was also designed by a stick shift driver, but I'll show you the automatic version in just a minute. So basically what we've got here, this is basically 2 devices that are associated to this SSID. You'll see it on your machine. It's called JuneCap after the grad student who did all the work. This is my phone, and this is my laptop. So you can see, for example, now if I go, if I basically go, oops, where did my web browser go? Well, let's just do it over here. Let's just go somewhere interesting. That's not interesting, but okay. So basically, you'll see this usage cap increase. Let's see if we can do something more interesting. Let's just grab a nice YouTube video or something. Let's just grab that guy. Okay, great, something good. Apologies for the noise during Nick's talk. I was testing my demo. So you can see here actually that this number here should start to increase. I think if basically we're on the right network. Yeah, so you can see it basically going up now. Great. What I can do, it's not on the screen here. Oops. What I can do here. Well, I'll do it on, shame. What I can do is set a cap. So for example, set device data cap. Okay, where are we? So I can say, okay, set this at 38 megs for the month or whatever. Right, so this is sort of a per device thing. Okay, so I guess now it's just gone over and essentially we're capped. I'm now off the internet effectively until I enable myself again. I can at least get myself to the portal. We fixed that problem. So that's essentially one of the things that we're working on with software-defined networks. Here is basically a version of. Oops. Are we there? Here's a version. Oops. Yeah. Here's a version of the interface that we're working on with the people who actually know stuff about this. And the idea here is, of course, like that what I showed you is going to look a lot more intuitive, right? Something that basically tells you, here's how much bandwidth you have left for the month. Here's basically how your usage breaks down by different devices. We're looking at things like, people have done user studies about, things they want about this type of thing. For example, I want to be able to give some of my usage cap to someone else in the house, or I want to be able to, budget this out so that at the end of the month, I can download all my software patches, or YouTube videos or MP3s or whatever, and things that basically help the user manage the network a bit better. Okay, so in conclusion, there are many problems in network management that result from the fact that configuration is low level and distributed. I've shown you one one system that we've been building using software-defined networks called Resonance that basically programs the network from a logically centralized control point and sort of views the network as an event processor, right? Something that basically just processes of different kinds of events from different devices on the network. This allows us to program the network at a higher level and also handle these dynamic events much more easily. It also allows us to cope with heterogeneity, right? Notice that, for example, in that demo, I had a laptop, I had an iPhone connected. I could have had something else, right? I could have had a set-top box. I could have had something else that generates events, or I could have had a third-party policy management thing that said, hey, look for the time of day and then install this kind of flow in the network and install this kind of flow table entry in the network and cut off Johnny at 9 p.m. A lot of things are possible here. This is just really the beginning, right? We're just starting to think about the types of things that we can do with this type of system. I presented 2 case studies here, but I think there are many more possibilities. So I thank you for your attention.